Hi, I'm Ben-Yaakov. This presentation is entitled Applying Omicron Bode 100 to Avoid Pitfalls when Applying High-Frequency Inductors in Power Electronics. Sort of a long name. Please note that the commercial inductors and the Bode 100 analyzer mentioned in this video are presented for educational purposes only. There's no endorsement and no rejection implied here. Now we're using inductors in power electronics in various applications, for example in buck converter or PWM converter in general. Here we have a switcher, a diode, inductor, and output section. And in the case of a CCM, that is continuous current mode of operation, the current through the inductor will have a DC component, and then there will be some ripple on it, depending on the duty cycle, the size of the inductor, and the frequency. Now, the other area in which inductors are used is in resonant or quasi-resonant or partial resonant converters, and in this case, the current would be more sort of a sinusoidal waveform. Here I'm showing an LLC converter. This is the resonant part, C sub R, L sub R, and L sub M. This is the LLC. There is a transformer here, an output section. And in this case, we're going to have, say, the resonant capacitor here, C sub R, sort of a sinusoidal waveform, depending on how close we are to resonant and, of course, the Q of the system. Now, inductors can be bought as commercial items or could be built. I'm here concentrating on inductors which are bought, that is commercial items, and I'm showing here two types. One is built around a toroidal body. It has a toroidal body, and then there's some windings around it. This could be a distributed gap type of a core. Usually this would be it. Or it could be an air-gapped core. Usually commercial inductors are not built this way in the toroidal form, but in fact this is the preferred way to go, but this is really outside the scope of this presentation. Now, on the other hand, we do have other type of inductors, and here I'm showing a Eaton component. This is based on ferrite. There is a core here, the cover, and this winding here, and of course one has to have an air gap in order to store the energy. These are inductors for power conversion systems. So there are various types of structures. I'm not showing all of them, of course, but perhaps these two are representatives. Now, the relevant parameters of the high-frequency inductors are really related to two subjects. One is the loss, temperature rise, maximum temperature you are allowed to go to, and then saturation. Now, these are actually based or dependent on the hysteresis curve of the core, being a ferrite or distributed or a iron powder core, and on the minor loop. Here I'm showing the minor loop. This will be the delta B, magnetic flux density deviation, and here we have the case of a this is like for a PWM converter in which there's a DC component. We are here, and this will be the minor loop here. And in the case of the resonant case, we are going to be, without DC, we are going to be around 0. And this is defining H and B, which are the axes here. This is H and this is B. This is related to the current, and this is actually related to the voltage. Now, the losses are dependent on the area here. The larger the delta B, the larger the area, the larger will be the loss. And then we have also a situation in which the mu, or the permeability, which is the slope here, the average slope, say, is changing as we change the operating point. And therefore, if we look at the inductance as a function of H, the operating point, the slope here is lower than this, and this will be a typical curve starting with 100%. This is the whole inductor, and then it's going down with H. Now, vendors are giving this information, and for example, Ferrous Cube is giving information about the core. This is a 3F3 material, and we see the mu, how it is changing, and of course, if you build an inductor around this material, this is the way the inductance will change, because the inductance is proportional to the mu. And then, of course, we have another way of looking at it, and here is, for example, the Eaton for the DR124. They are showing here percent change in the inductance, and here we see that as the percent saturation, which is defined as the actual current times some value that they call the saturation, then as this ratio is increasing, the percentage, then of course you'll have eventually a drop in the inductance. This is the open circuit inductance, and there's a mistake here. So this is 85 degrees. It's temperature dependent, which is not shown here, and this is temperature dependent. So as you're approaching this value I sub, which they define, of course there is a larger drop. And then we have another issue, and that is the resistance of the wire. Now, of course, copper, which is usually the material that is used for the wire, has some resistance or specific resistivity, but at high frequency we do have the skin effect. This is the approximate expression for given temperature and material. This is for copper, and this is in millimeters, 72 over square root of f in hertz. So in 100 kilohertz, we are talking about 0.23, about millimeter, meaning that if the diameter is twice this value, then actually you are using all the area, and therefore the resistance will increase. That is, this is the maximum point that is 0.4, so 0.5 millimeter is the maximum diameter that you will use for 100 kilohertz. Actually, you like to have it smaller than that, because otherwise you're going to have the problem of larger AC resistance. That is, the resistance for the high frequency will be higher. Then we have also the proximity effect, in which when you have two wires with carrying current, then the charge carriers also push the side, and this is also reducing the surface, the area that is available for the high frequency. This is more complex. It has to do with the structure of the device, the number of layers, etc. I'm not going to go into it, just to mention that this is something also that should be taken into account. So, aside from the fact that you have our AC and our DC, there is also the effect of temperature. As the temperature goes up, then the resistance of copper or any other material, in the case of copper, is going up, and it's about 0.4% per degree centigrade. So if the inductor is heating up or the temperature goes up, then it could be a fairly large difference for the resistance. Now, if I know the resistance, our DC, our AC, then I can calculate the copper losses, and which will be this is the loss due to the DC. This is, of course, I have to correct for temperature here. This is the loss for the AC, IRMS of the AC. In the case of, say, a PWM converter with a DC component and a ripple, and I'm assuming that this is a triangular shape, then it will be I peak to peak. This is I peak to B over 2. This is one side. And then square root of 3 squared. This will be the I squared. This is actually, this is IRMS square. I'm sorry, it should be square here. Now, the delta B, the deviation, the high frequency component of the magnetic flux density is causing, as we've seen, there's the minor loop, it's causing losses, and this is typical. This is actually a sort of a fitting of data to the so-called Steinmetz equation, or modified, I should say, Steinmetz equation. And these curves actually show you the core loss. In this case, it's already for this particular core, that's this Eaton core, DR124, as a function of, in this case, peak to peak. Usually it's B peak, but in this case, they give it as peak to peak. And therefore, if you know, say, the B peak to peak in Tesla or millitesla here, 100 millitesla, and you know the frequency, then you can find out what is the core loss, the total core loss of this device, and this should be, of course, added to the copper loss. Now, one has to bear in mind that these curves are dependent also on temperature, and therefore you have to look up and see this particular material that the inductor is built around, how is it dependent on temperature. And I'm showing here two cases. One is for 3F3, which is optimized, so to speak, at the high temperature. So you see this is now the loss. Now this is for the material, core material 3F3. So it's in kilowatt per meter cube or milliwatts per centimeter cube. And this is degrees centigrade. And this is for different situation, frequency, and this is B peak, actually, for sinusoidal actually excitation. And you see that, for example, let's take an extreme case here, 200 kilohertz, 100 millitesla. You see there is a minimum here at 90, 95, 100 degree actually, centigrade, while here at a lower temperature it is much higher. So in this case it's better to work at a higher temperature. Anyhow, the point that I'm making is that you have to look at this temperature dependent to know for the specific inductor and the intended operating temperature what would be the losses, and as I'm showing here, that the difference could be fairly large, more than twice. And here it is for the case of a 3691. This is a low temperature material, and the minimum here is at around 60 degrees, say. Okay. So we have the copper loss, we have the core loss. The question is, how do we estimate the delta B that we need to look up these curves? So in the case of, say, a PWM, a converter, we can use this relationship. V is M defeated T, taking out the area, and we found that delta B, or delta B, say, peak to peak in this case, is 1 over NAE V T off. This is V delta T. This is okay. This is during T off. The current is flowing this direction. This is a short here. So the inductor is exposed to V out. I'm neglecting the voltage drop on the diode. So therefore the volt second here, volt second, is V out times T off divided by this will give you delta peak to peak, and this is this delta peak to peak here. Now, there's another way to go around, and some vendors are actually going this way, and that is to relate this equation that I've written before to VL di dt, and this Ampere law, and then sort of looking at the two sides, you come up with this equation. In this case, delta B is a function of the same, this is the area and number of turns, but then you have here the inductance and delta I peak to peak. Unlike this case that you have no inductance, only V out and T off, here you have L. These two are exactly the same. This is actually the same relationship. You're just moving around the parameters and the some algebra, and so therefore you can use this equation, and it is, some vendors call this K. We'll see it in a minute, and from this you can calculate delta P, then go to the curve and see what is the power loss. In this case, this is this curve here during T off, this delta I here. Okay, now in the case of a resonant converter or an inductor intended for resonant converter, the situation for core losses are much, much, much worse. And it should be emphasized that the delta B is much larger because there's no DC. It's not just a question of a ripple, but the whole waveform is sort of around zero voltage and current, and therefore you have to look up this waveform and find out, say, from B is related to V, find out what is B and delta B, and then you can use either this equation, okay, this will be like cosine minus cosine V peak and this thing, or 1 over omega, of course, and here you can use this equation. Again, you need to estimate delta peak to peak from the voltage or, in this case, the current peak to peak of this element. And as I've said, in the case of resonant converter, the situation is much, much, much worse. Okay, now once you have the losses of the copper, losses of the core, taking everything into account, then you can go to a curve like this, which not all vendors are actually providing. We'll see it. And this is a temperature rise of a given inductor. This is a commercial Eaton inductor DR124. And for a given power, you see what is the delta T. This for the hot spot, actually, supposed to be the hot spot of the inductor. And so therefore you can estimate the maximum temperature rise above the ambient. So you need for this, of course, estimation of the losses. Now, another issue that you have to take into account is that in between the windings there is a capacitance, so you can actually represent in the lump model an inductor plus a parallel capacitor, and therefore if you look at the impedance of the inductor, what you see is that at the very beginning you see mainly the so-called ESR, which is sort of something approximate, and there is then a resonant point in which the impedance is very high. Obviously, above this point, this device or element does not behave as an inductor. So this is the maximum operating frequency just from this point of view. There's other restrictions. So this capacitance in between the windings is causing this resonance and therefore limiting the frequency you can use a given inductor at high frequency. Now, looking up therefore the requirement for designing a system with an inductor, or the parameters that you have to know or take into account, we see that there's quite a bit of a list. We have the inductance, saturation current, the dependence on the inductance on the current, RDC as a function of temperature, RAC as a function of frequency. We need this K, which is this parameter that allows us to go between the delta, say I, to the delta B. So we can calculate, we need the curves for relating delta B to the core loss, and then we need to know how this depends on temperature. And of course, we can then, knowing the total loss, we need information of how the temperature of the element will rise with the total loss. And then we need, of course, to know what is the allowed maximum temperature and the resonant frequency. It's quite a number of parameters that we do need in order to do a sort of a correct design with an inductor. So the question is, how do manufacturers really fare? And I'm now bringing two examples. One is really very meager with very little information, and one is more information. So let's have a look at these. So let me start off with the Triad element. And as you can see, this is this form. Actually, this would be probably iron powder core, could be different materials, and it's a distributed gap as we call it. And what we see here, that this particular element is given the parameters or the information given are what is the inductance at the bias, I guess it is the DC amp, the rated amp, and then max of DCR, that is the resistance, 42 milliohms. This is DC only. And then there is some dimensions and weight. And what it says here, that operating at rated current yields approximately 40-degree temperature rise over 20-degree ambient. Well, 40-degree temperature rise, you don't have to say the 20-degree, but 40-degree temperature rise. But the question is whether it's delta 40 or 20. Well, doesn't matter because it's insufficient information, because it's only 40-degree, and they're just talking about the rated DC amps. That is when you operate this inductor at DC. This DC, well, inductor is not going to work with DC. It will have an AC component, and we have very little, if any, information of what really happens at high frequency in terms of the losses. The only thing it says that the no bias inductance was measured at 10 kilohertz. Well, doesn't mean. Well, they are saying that this is specified minimized transient, and this is used in high frequency circuits, but there's very, very little information. Okay, so let's have a look now at another device, another inductor, commercial inductor. And this will be the DR124 that I've already mentioned. This is a Eaton, this is the company. This is the Eaton device, and this is how it looks. It's a family of inductors, and it says that the operating range is 40 to 125 ambient plus temperature rise. So 125 is the maximum temperature allowable for this element, which is one important information. And then they have, it's a table, there are different models here for different inductances, and what they give is the rated inductance, open circuit inductance, okay, I RMS, this is the intended RMS, I saturation, this is an arbitrary point in which the unit is already saturated, DCR, DC resistance, and also very nicely DCR at plus 20 degree. So you see that the resistance is going up from 2.2 to 2.7 in 20 degree, but 20 degree is very small because this unit can go to 125. And then they have this K factor, which I've mentioned before, which is very nice. And this K factor, they're saying, let me just increase it. They're saying this B peak to peak is K, this is this number, L delta I. So you can estimate B peak to peak, and once you do that, they actually provide, let's have a look here, they provide this curve, this plots, which I've already mentioned or showed, and this, once we have the B peak to peak, you can find out what is the core loss for the specific application that you have. They also have the increase of the temperature as a function of the total power loss. This will be copper plus core losses, so you can estimate the temperature rise. There is no information about the temperature effect of these losses. Now looking now at the checklist that I've prepared and comparing the Triad inductor to the Eaton device, we see that in case of the Triad inductor, we are missing a lot of information. Many parameters are just not given. What is given is just the inductance, ISAT, and RDC, and in many applications this will be not sufficient actually to estimate the performance of the inductor in the application, certainly not for high frequency DC to DC converter. Now in the case of the Eaton element, we do have quite a bit of information. Missing, however, is RAC as a function of frequency, the dependence of the core losses on temperature, and the resonant frequency. Out of the three, this is the most important one, the RAC, because it will limit the operation of the unit at high frequency, especially if we want to have a large ripple, or if the design calls for higher ripple, or if it is a resonant converter, then RAC becomes extremely important. So here comes to the rescue a Omicron Bode 100, which is a network analyzer and has a fixture for measuring inductances and, as a matter of fact, capacitors. So here is the fixtures. We see that it is connected to the analyzer by the 3 cable. This is the excitation and then A and B. And it has actually a unit here for calibration. So you first calibrate it to get the zero level of the instrument plus the fixture. And then you can run analysis of a given element. And here we did this for the inductor. This is the Eaton inductor, and this is now the result for the impedance. The red one is the impedance, the red curve, the impedance, and the blue one is the phase. Now the impedance starts fairly flat, and this is because we are at the low frequency area in which we have a resistive behavior, and then of course we have omega L. This is the inductor, this is a log scale, so this is why it is a straight line. And then we come to the peak value. This is the resonant of this element, beyond which of course you wouldn't like to work, because you are losing all the inductance behavior. So the operation region will be up to, say, 2 megahertz, if you'd like to work up to there. Now we see the phase here. Phase is here. This is 0. So it sort of starts with 0 at very, very low frequency. And then it approaches, of course, the 90 degree. But it is not 90 degree. It is 87, because here we have both an inductance and a resistive component. And in fact, knowing the total impedance and knowing the phase, you can calculate each component, but really you don't have to do it, because the Bode 100, this instrument, will do it for you, and here it is. So here we see the 2 components. We see the inductance. This is about 100 microhenry, this particular unit. Here is the resonance. So we see here quite a bit of a change, and of course this is not a useful region, and we are talking about, say, 1-2 megahertz. But lo and behold, see what happens to this part. This is the resistive part, the passive part, the resistive part. And what we see here, that it started fairly low values, and then it starts to shoot up at about 10 kilohertz, and above 100 kilohertz, well, it goes very high. Now at the very low frequencies, say 1 kilohertz, here it is 280 milliohm. This is about the value that the vendor, the manufacturer, is actually giving in the datasheet for this particular unit, about 280 milliohm, and this is at low frequency. But say at 100 kilohertz, it is already 2.3 ohms, so almost a factor of 10. Now, not to mention that beyond that, let's say if you work at 120 or 200 or 300 kilohertz, then of course you're going to have very, very large resistances. This is the scale of the resistance. So this is the resistance. And obviously, if you have a appreciable ripple in the case of PWM, or if you work in resonant converter and if the frequency is high, you are in big trouble. So without this information and assuming that everything is okay, you might get into real trouble if you ignore this aspect. So the ESR is sort of a representation of the resistive part, but note that if you are modeling the inductor as the inductive part plus ESR, this ESR is also including core losses, because you have two parts, the resistive and inductive, and when you look at the analyzer output, this resistive part is a lump value for everything. So just to make sure that in this case we are really looking at the copper losses and the effect of the frequency of the copper resistance as a function of frequency due to the skin effect, we have run this analysis a number of times with different magnitude. And the rationale is that if the ESR here is dependent on core losses, or if a large part of it is dependent on core losses, then obviously as you'll increase the excitation, delta B will increase and you'll see a difference, okay? If you don't see a difference, it means that your excitation is low enough so the copper loss, the resistive part of the conduction part, is the dominant one. So here we have a sequence of the same analysis with different excitation values. Now 0 dB here is about 0.3 volt on the inductor, which is fairly small for the inductor. And we go from minus 30 dB to 13 dB, and we see that it is just about the same. This would imply that what we see here is primarily the copper part and not the core part. So it is probably due to the skin effect and perhaps some of the proximity effect. Now here we see the inductance part, and interesting that at the very high excitation, or the relatively high excitation, 13 dB, we see already a small change, which is due to the behavior of the hysteresis curve, HB as a function of H. So we see here some changes, but this is not the point I'm driving at. I'm looking at the losses here, and the conclusion, as I've said, is that we see here primarily the copper loss and the change of the copper resistance with temperature, that is the RAC component. So to summarize here, we see that the resistance goes from 280 milliohm to 2.5. Inductance is changing, but really not that much. Now, to verify the question of this skin effect, we have measured the diameter of the wire. Here is the inductor. We've taken it apart, or I might say broken it. And here's the wire. And we measured the wire, and it turns out that the wire is 0.25 millimeter, okay? So with a wire of 0.25 millimeter, the maximum frequency that you can operate at is 83 kilohertz. This is when the sort of the skin effect or skin width is sort of taking over, okay? So 0.25 will be then twice the skin width. So the practical range of operation is up to 83. Actually, you have to be a little bit lower than that, and we can see it here very clearly. At 83 kilohertz, we are somewhere here, which is already bad news, and you'd like probably to be here, unless of course the ripple is very, very small, or the AC component is very small, so you don't have to worry about it. But if you do have an appreciable ripple and a large AC component, then of course you'd like probably to go to a few tenths of a kilohertz and even not approach the 100 kilohertz. So this would be the conclusion based on this Bode 100, the Omicron L analysis, which is very, very useful, and without it, you really don't know what is happening. Now, this information is very seldom given by a vendor or manufacturers of inductors. So this is something that if you really do want to do a good design, you do have to test and check yourself, because as I've said, this information usually is not found in datasheets. So the conclusion is that high frequency inductors, well, there is more than meets the eye. They are not simple. There are many, many parameters, and if you like to do a decent design work, you do have to look at all these parameters and see how they affect your design. Now, not all of them are important, perhaps in a particular case, but they could be, especially if you work at high frequency and if the ripple is high, or if you're working at resonant or resonant converters. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it interesting, and perhaps it will be useful to you in the future. Thank you very much.